Welcome all. This is a presentation on the subject Computer System Design and Architecture 06CS6043, which is a subject offered to the first semester MTech in Computer Science and Information System students under KTU. Myself Harikrishnan M, Assistant Professor in the Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. We've already covered the first part of the first module in a previous presentation. In this particular presentation, we'll be dealing with the second part, which is highlighted here. So we'll start with trends in technology and power. We'll talk about dependability, how performance is measured, some of the benchmarks that summarize performance, Amdahl's law, and then overview of computer architecture processor performance equation, performance evaluation of processors, and some numerical exercises on Amdahl's law and performance. So we'll start with the different trends in technology. There are four important technologies that are critical to modern implementations. First is the integrated circuit logic technology. Then you have the semiconductor DRAM, magnetic disk technology, and network technology. These four technologies are very critical because of the role they play in the implementation of modern technologies. Bandwidth or throughput and latency or response time are two terms that you have to understand and know in order to work out some of the numerical problems that are coming up in this particular module. By bandwidth or throughput, we mean the total amount of work done in a given time. It is usually expressed in megabytes per second for disk transfer, for example. Latency and response time, on the other hand, is the time between the start and completion of an event. For example, milliseconds for disk access. Now, a simple rule of thumb that is followed in relation to these two terms is that bandwidth grows by at least the square of the improvement in latency. The graph shown here is a log-log plot of the bandwidth and latency milestones relative to the first milestone. So it can be noted here that as the latency improved from 6 times to 80 times, the bandwidth correspondingly improved by about 300 to 25,000 times. So this image was taken from the textbook by Patterson. Now talking about the trends in power in integrated circuits, we all know that power must be brought in and distributed around the chip. The modern microprocessors use hundreds of pins and multiple interconnect layers just for power and ground. The power is dissipated as heat and therefore it must be removed because overheating can cause issues to integrated circuits. For CMOS chips, the traditional dominant energy consumption has been in switching transistors. This is also called the dynamic power. So the dynamic power is calculated as the power required per transistor is proportional to the product of the load capacitance of the transistor, the square of the voltage and the frequency of switching. And the unit of the dynamic power is watts. The equation for calculating power and energy are given here. Power is calculated as half times capacitive load into the square of voltage into the switched frequency. And the dynamic energy is calculated as capacitive load into square of voltage. The unit of energy is joules. Now we will work on a small numerical problem here. The question here is, some microprocessors today are designed to have adjustable voltage so that a 15% reduction in voltage may result in a 15% reduction in frequency. Now what would be the impact on dynamic power? We know that here, since the capacitance is unchanged, the answer to this question is the ratio of the voltages and frequencies. We know that the ratio of the new power to the old power is calculated as voltage into 0.85 the whole square into frequency switched into 0.85 divided by voltage square into the switch frequency. Here we use the value 0.85 because there's a 15% reduction. So the remaining percentage is 85. So it is necessarily 0.85. So that gives us the answer as 0.85 cube, which is necessarily 0.61. So what this basically says is the impact on dynamic power is that the power is reduced to about 60% of the original. Talking about the trends in cost, the underlying principle that drives costs down is the learning curve. That is, the manufacturing cost decrease over time. So the trend in cost or the learning curve for cost is best measured by the change in yield. Yield is nothing but the percentage of manufactured devices that survives the testing procedure. Another key factor in determining cost is volume. Here the rule of thumb that is followed is cost decreases about 10% for each doubling of volume. Now the cost of an integrated circuit, the cost of a die, The number of dice per wafer and the die yield are calculated using the equations given here. Now based on these equations, we'll work out a small problem. The question here is, find the number of dice per 300 millimeter wafer for a die that is 1.5 centimeter on a side. Here the die area is 2.25 centimeter square because the die is actually 1.5 centimeters on a side. So therefore the dice per wafer is calculated using the given equation and you'll get the answer as 270. Another problem on the same equations. Find the die yield that are 1.5 cm on a side and 1 cm on another side, assuming a defect density of 0.4 per centimeter square, and the value of alpha here is 4. So the total die areas given are 2.25 cm square and 1 cm square. For the larger die, that is the die that is 1.5 cm on a side, the yield is calculated to 0.44, and for the smaller die the yield is calculated to 0.68. That is, less than half of all the large die are good, but more than 2/3 of the small die are good. Now what do you mean by dependability? All system that operates properly should be dependable. So to decide whether a system is operating properly, infrastructure providers of the system have started offering service level agreements or service level objectives to guarantee that the networking of power servers is dependable. Systems alternate between two states of service with respect to a service level agreement. One is service accomplishment, the other is service interruption. Transition between the two states is caused by failures or restorations. There are two main measures of dependability. One is the module reliability and the other is the module availability. Module reliability is a measure of continuous service accomplishment from a reference initial instant. Mean time to failure is a rate of failures, that is failures per billion hours of operation or failures in time. Mean time to repair or MTTR is simply the service interruption, and mean time between failures or MTBF is the sum of MTTF and MTTR. Module availability, on the other hand, is a measure of the service accomplishment with respect to the alternation between the two states of accomplishment and interruption. Module availability is calculated as the ratio of MTTF to the sum of MTTF plus MTTR. Now how do you measure, report and summarize performance? Most computer users are interested in reducing the response time, that is the time between the starting and completion of an event. It is also known as the execution time. So we all require that the execution time should be as less as possible so that we get instant results to whatever operations or events are performed. The administrator of a large data processing center, on the other hand, may be interested in increasing the throughput, which is the total amount of work done in a given time. So when you talk about a phrase computer X is n times faster than computer Y, what we actually mean by that is, here n is the execution time of Y divided by the execution time of X, or the ratio of performance of X to performance of Y. So this ratio is used to predict whether a given computer X is n times faster than a given computer Y. So the execution time and the performance plays a huge role. The performance gain that can be obtained by improving some portion of a computer is calculated using the Amdahl's law. Amdahl's law defines the speed up that can be gained by using a particular feature. The speed up is calculated as performance for the entire task using the enhancement when possible divided by performance for the entire task without using the enhancement. Alternately, you can calculate the speed up as the ratio of execution time for the entire task without using enhancement to the execution time for the entire task when enhancement is possible. The Amdahl's law gives us a quick way to find the speed up from some enhancement, which depends on two factors. One is the fraction of the computation time in the original computer that can be converted to take advantage of the enhancement. The other is the improvement gained by the enhanced execution mode. That is how much faster the task could run if the enhanced mode were used for the entire program. Now a numerical problem on Amdahl's law. Suppose that we want to enhance the processor used for web serving. The new processor is 10 times faster on computation in the web serving application than the original processor. Assuming that the original processor is busy with computation 40% of the time and is waiting for I/O 60% of the time, what is the overall speedup gained by incorporating the enhancement? Here fraction of enhancement is calculated as 0.4, which is 40%. Speedup of enhancement is 10. Now the overall speedup is 1 by 0.6 plus 0.4 by 10, that is 1 by 0.64, so you get the overall speedup as 1.56. The processor performance equation. Essentially all computers are constructed using a clock running at a constant rate. These are known as ticks, clock periods, clocks, cycles or clock cycles. Computer designers refer to the time of a clock period by its duration or by its rate. CPU time for a program can be expressed in two ways. One is the product of CPU clock cycles for a program and the clock cycle time, and the other is the ratio of clock cycles for a program and the clock rate. The number of instructions executed is the instruction path length or the instruction count. The clocks per instruction or CPI is calculated as a ratio of CPU clock cycles for a program and the instruction count. Now these were the references used to prepare this presentation. Computer Architecture, a Quantitative Approach by John L. Hennessy and David Patterson. Advanced Computer Architecture, Parallelism, Scalability and Programmability by Kai Huang and Naresh Jotwani. Memory Systems, Cache, DRAM and Disk by Bruce Jacobs, Spencer W. Ng and David T. Wang. Parallel Computer Architecture, a Hardware or Software Approach by David Culler, J. Pal Singh and Anup Gupta. Thank you all for the patient listening.